In this video, I'm going to go over chapter 9, section 4, which is testing a claim about a difference between proportions. So we're going to use the example below to go through each of the 4 steps of doing this lesson, which is essentially the same ones you've been doing since we've talked about confidence intervals, but we do get a new formula here for checking the large counts condition in step 2. So a teacher has 2 large containers filled with blue, red, and green beads, and claims the proportion of red beads is the same in each container. So we're looking at red beads. The students believe the proportions are different. Okay, so the students believe the proportions are different is going to end up being our alternative hypothesis. So she says they're the same. So our null hypothesis is that the proportion's the same for red. And then our alternative hypothesis is going to be that it's different. Each student shakes the first container, selects 50 beads, counts the number of red beads, returns the beads into the container. The student repeats the process for the second container. So there's taking out 50 beads for both. So that means that our sample size for container 1 is 50. And our sample size for container 2 is 50. Okay, so that value for n is the same for both containers. So for 1, student samples contain 10 red beads from the first container. So x1 is going to be 10. And then 16 from the second container. So x2 is going to be 16. Let P1 be the true proportion of beads in the container 1 and P2 be the true proportion of beads in container 2. So they're telling us what the parameters are. So notice that in step 1, we have to state the null and alternative hypotheses and the parameters. So in this case, they're giving us P1 and P2. Again, mostly because it's multiple choice so that we only have to select one item. We're only selecting the correct null and alternative hypothesis. Remember that in these problems, the null hypothesis is always going to be the same. So H sub 0, our null hypothesis, is equal to P sub 1 minus P sub 2 equal to 0. Remember that they say that they use this one because it could be something different. So if it didn't say that they were the same, if it said that like it was too big or something, you would have a number there. And then the alternative hypothesis is one of these 3 options each time. And so remember that because ours says that it differs, that it's different, we're picking not equal to 0, okay? And so that means that we're gonna have to do a 2-sided p-value. And so when we're looking at the p-value, we're actually gonna double our number based on our z-score or z critical point there. Okay, so that's the first example. So we're looking for the option that has H, the null hypothesis as P sub 1 minus P sub 2 is 0, and the alternative hypothesis that states P sub 1 minus P sub 2 is not 0. Next, we're going to have to name the test and check the condition. So remember that there's 3 different names for this test. So it's either a 2-sample Z for P1 minus P2, a 2-proportion Z test, or a Z test for 2 proportions. So if you have a question that asks you to name the test that you would use, it's one of these 3, nothing else. So the conditions that we're checking is random. So we must have 2 independent random samples, so they're separate from each other, or data from 2 groups in a randomized comparative experiment. So in this case, the fact that it is randomized is in the idea that they shake the container. So shaking the container makes it random. So it meets that condition. So then notice that they return the beads to the container. So that means that it is done with replacement, which means that the 10% condition is not applicable. And so it's only applicable if they don't replace the beads for each sample. Okay, so we've met the first two conditions. We're going to look at large counts. So in large counts, it changes a little bit. So notice that I have 4 things I have to check because again, I have 2 separate samples. So I'm checking sample size times this p hat sub c. So that value is determined using the formula x1 plus x2 over n1 plus n2. So remember, we found those values here. So we're going to do 10 plus 16 over 50 plus 50 to calculate this value. So 10 plus 16 over 50 plus 50 gives us 26 over 100, which is 0.26. Notice that N1 and N2 are both 50. So really, I only have to check 2 of them in this situation. So if I'm going to multiply, I have to take 50 times 0.26, which gives us a value of 13. And then I have to check 50 times 1 minus 0.26, which is the same as having 50 times 0.74. And that gives me a value of 37. So remember that I'm checking, are these greater than or equal to 10? So it works there. Again, I only have to check 2 because these 2 values end up being the same, and these 2 values end up being the same just because our sample size was the same. So if N1 and N2 were different, I would have to check all 4. Okay, so we've met all the conditions, which means that we can use this test. So all conditions met. Okay, so the next step is doing or performing the actual test. So to perform the test, we have to find the test statistic, so the z-value, and use the z-table to find the p-value for this hypothesis. Okay, so remember, because it's not equal to, we're going to do 2-sided, which means that when we find our z-value, the negative version and the positive version, we're going to have to double that p-value for one of those z's. So we didn't actually figure out p hat 1 and p hat 2. So p hat 1 is our x1 divided by n1. So it's 10 over 50. P hat 2 is going to be the 16 over 50. Okay, so 10 over 50 is 0.20, and p hat 2 is the 16 over 50 is 0.32. Okay, so in our formula then, we've got 0.20 minus 0.32 over the square root of, so remember this value is the 0.26, and then 1 minus that is the 0.74. Okay, so when I plug into here, I'm doing 0.26, and then 1 minus 0.26 is 0.74. So 0.26 times 0.74 is both of these numerators. And then remember that our sample sizes are both 50, so these are actually going to be the same value. So what you can do is just calculate that fraction, so 0.26 times 0.74 divided by 50, and double that number. So either way, we're going to end up with negative 0.12 over the square root of 0.007696. And so if I calculate that, I get negative 1.345. So I'm going to say that my Z value then, my critical, test statistic is negative 1.35. Okay, so what this means is that these two values are negative 1.35 and positive 1.35. I always want to look up the negative one on the Z table because it's shaded in the right direction. And then I know that the positive one is just the same amount because it's symmetric and those are the same value. So if I look up negative 1.35, negative 1.35, that's going to give me 0.0885. So I'm going to put 0. So this value, this area is 0.0885, and that's true for both of them. Okay, so then our p-value, because it's a two-sided, a not equal to, is going to be 2 times 0.0885, which gives us an answer of 0.177. So those would be the two answers that we were looking for for the multiple choice question. Okay, so again, if this was just less than or just greater than, our answer would be the 0.0885. Because it's not equal to, we're doubling that value. Okay, so we're going to use that p-value to draw the correct conclusion. So using our hypothesis test, we got a p-value of 177, and they want us to use alpha equals 0.05. So we're comparing those two values. So if this is greater than alpha, that means that we are going to fail to reject our null hypothesis. So what this means is that there is insufficient evidence that that alternative hypothesis is true, so that there is the true proportion of beads, red beads, is significantly different in each of the two containers. So notice that if these were different, if it was less than, we would reject, and it would be the opposite. Okay, so just depending on that p-value compared to the alpha value tells you whether you're going to reject or fail to reject that null hypothesis.